Hi, welcome to office hours, virtual office hours that is. Today we're going to start with a very interesting problem. Consider a point moving relative to a rigid body which is itself rotating around a fixed pivot. The game, calculate the velocity of the point with respect to the fixed coordinate system. Check this out. Consider a point moving relative to a rigid body which is itself rotating with respect to the ground. We would like to find the velocity of the point with respect to the ground. To see how to do this, let's consider these motions one at a time. First, assume the rigid body is not rotating, and consider the point, here labeled B, moving along some path on the rigid body. As the point moves along the path, it has a velocity with respect to the rigid body. We'll call this velocity VREL to reflect the fact that it is a velocity relative to the rigid body. Obviously, if the rigid body is not moving, it's also a velocity with respect to the ground. Now, assume that the point stops moving with respect to the rigid body, and the rigid body begins to rotate. The rigid body rotates about a fixed point O with an angular velocity omega measured with respect to the ground. Clearly, the point has some velocity with respect to the ground resulting from the rigid body's rotation. So, how to represent both these motions? How can we find the velocity of point B when the point is moving relative to the rigid body and the rigid body is moving with respect to the ground? We begin by defining a body coordinate system that is attached to the rigid body and rotates with it. We define the position of point B with a vector r and express it in terms of the body coordinate system's unit vectors I hat and j hat. To find the velocity, we differentiate using the product rule. Rearranging, we see that these two terms are simply the point's velocity with respect to the body coordinate system, that is to say, with respect to the rigid body. This is simply VREL. It is also sometimes written like this, or like this. These two terms involve the derivatives of the unit vectors. We recall that di hat dt is equal to omega j hat, and dj hat dt is equal to minus omega I hat. When these are substituted, the result can be seen to be equivalent to omega cross r. So, the velocity of the point with respect to the fixed coordinate system consists of two components. VREL, the contribution from the point's motion with respect to the body coordinate system, and omega cross r, the contribution from the rotation of the rigid body. All right, so there you go. Now, the nifty thing about that formula is that not only can it differentiate position to get velocity, we can use the very same formula to differentiate again to get acceleration. All right, now in this next segment, we're going to use those formulas to calculate accelerations for the purpose of determining normal force and an equation of motion. Check this out. All right, so here's the problem. We have a bar rotating around a fixed pivot with an angular velocity omega and angular acceleration alpha. On the bar is a collar of mass m that slides along the bar's length. The distance of the collar from the pivot is described by the scalar length r and its derivatives. He forgot to mention that there's no friction between the bar and the collar. The system is frictionless. The question, given these, find, number one, the normal force, the force the bar applies to the collar, so-called normal force because it occurs perpendicular to the plane of contact. The second is write an equation of motion that describes the motion of the collar. What this will be is a differential equation in terms of r and its derivatives. That's the game. Here we go. Here's how we're going to do it. We begin by choosing an intermediate frame, small I hat and small j hat, in the direction along the length of the bar and perpendicular thereto. Second, we use the now familiar to you equation for the acceleration of the point on the moving body. Alpha cross r minus omega squared r plus 2 omega cross v rel plus a rel. Okay, having chosen the directions of I hat and j hat, we're in a position to write the angular velocity as a vector. Its magnitude times k hat. Similarly with the angular acceleration. We also recognize that the position of the point is given by r times I hat. V rel, the motion of the point with respect to the rigid body, is r dot I hat. Similarly, the acceleration is r double dot I hat. When we plug these vector quantities into our well-known equation for acceleration, we get this, that the acceleration of that point is r double dot minus r theta dot squared in the I hat direction, and in the j hat direction we have the terms r theta double dot plus 2r dot theta dot. Now, what these are this is the acceleration of that point in the I hat direction and in the j hat direction. And what I've done here is I've drawn these components. You see in the I hat direction, r double dot points in that direction, r theta dot squared in the opposite direction. Similarly in the j hat, r double dot in the plus j hat and 2r dot theta dot in the j hat as well. The normal force, and now what we do is sum forces in each of the two directions and apply Newton's laws, F equals ma. In the j hat direction, the normal force is in the positive direction, and that's equal to the mass times the acceleration. So this is the answer to the first question. What's the normal force? The second is summing forces in the I hat direction. We get r double dot minus r theta dot squared. He actually skipped a small step there. When you sum forces in the I hat direction, you actually get m r double dot and m r theta dot squared respectively. The m subsequently cancels out and gives you the result he's shown there. Equals 0 because there's no external forces. This is the equation of motion in R, a differential equation in R. That's it. All right, so there you have it. That's it for this week. See you next time.